Good morning, everybody. At least it's good morning for me. So you guys are along for my ride. Today we are continuing on looking at energy, okay? And we are concentrating in on the second law of thermodynamics. Now, we think about the second law of thermodynamics. It states that for a process or a reaction to be spontaneous, the change in entropy of the universe must be positive. This doesn't mean that a process can't be forced to happen to be non-spontaneous, but if it is non-spontaneous, the change in energy of the universe is going to be negative, and it's going to have to be a forced situation. Okay? So the entropy of the universe can be thought of as being made of two parts: the change in energy of the system and the change of energy of the surroundings. Remember, as we're looking at energy, we're always looking at system and surroundings. Okay? In our case, the system is going to be some chemical reaction that takes place in a beaker. So calculating delta S of the system is easy. We can use Hess's law. Okay? But how do we get delta S of the surroundings? That's going to be a little bit harder. We're not doing things directly with the surroundings. So we want to think about things that we can measure in the system that are going to give us an indication of what's going on with the surroundings. What type of changes will be going on in the surroundings as a result of the changes happening in the reaction? Well, first thing we know is between a system and the surroundings, heat will be flowing into or from the surroundings as the system either absorbs energy, which would be into the system and out of the surroundings, or releases energy. That's energy coming out of the system and going into the surroundings. So if the system gains, the surrounding loses. If the system loses, the surroundings gain. Okay? If the heat is flowing to the surroundings, which means that the reaction is exothermic, there's more energy now in the surroundings, so we get an increase in entropy because the particles are going to be moving more. And if heat flows from the surroundings into the system, from the reaction point of view, we're looking at something that's an endothermic reaction, then there's a decrease in energy of the surroundings, and we get a decrease in entropy of the surroundings. So that we can say that the change in entropy of the surroundings is proportional to the change in enthalpy of the surroundings, which makes it proportional to the negative of the change in enthalpy of the system. Okay? So the change in entropy of the surroundings can be gotten at by looking at the change in entropy of the system. Now notice it says proportional to. So we're not quite all the way there yet. At a lower temperature for the surroundings, this enthalpy change is more noticeable than at a higher temperature. Now think about kind of having 3-year-olds. You got 2 3-year-olds playing, you got a certain amount of chaos. Okay? If you add a third 3-year-old, you have an exponential increase in chaos because they have to figure out how to get along and play together. But if you already have a room full of 10 3-year-olds and all kinds of chaos, adding an 11th one in isn't going to seem like that much of a change. Okay? So at low temperatures, any energy flowing in or out is proportionally more important. So change in entropy of the surroundings is proportional 1 over the temperature in Kelvin. So if I combine these two proportionalities together, what we get is that change in entropy of the surroundings is equal to negative delta H of the system over T the temperature in Kelvin. Okay? So now we have a way to calculate the entropy change of the universe by looking just at things that happen in the system. So delta S of the universe is equal delta S of the system minus delta H of the system over T the temperature in Kelvin. And by calculating delta S of the universe, we can decide if a system is spontaneous or not. If delta S is positive, we have a spontaneous process and energy will be released as the reaction happens. Okay? If delta S of the universe is negative, we have a non-spontaneous process and energy will be needed to maintain the system at its present state, and even more energy is needed for it to go in the forward direction. Note, if no energy is provided to the system, the process will run in reverse and release energy and move toward equilibrium. If delta S of the universe equals 0, then we have a non-spontaneous process because it's at equilibrium. There is no direction to move that's going to release energy, okay? And no energy is needed to maintain this position. Okay? So, let's think about the following. Just because a process is non-spontaneous does not mean we can't make it happen. It just means that it requires an input of energy from somewhere else to take place. We need to force a non-spontaneous reaction to happen. Okay? Which means if something becomes more ordered, something else has to become more chaotic. If we're interested in determining which reactions are spontaneous because they release energy and we can use that energy to do things to drive other processes. Okay? Now, an example of using a spontaneous reaction to make something else happen, think about burning fuels. Gasoline. It converts chemical energy spontaneously into thermal energy. And then that thermal energy of expanding gases is converted into mechanical energy, which makes a machine move. Your car is not going to go anywhere if there is no fuel combusting in the engine. Okay? We also need to be able to determine how much energy as useful work we can get out of a process or a reaction, or the minimum amount of energy we need to put into a process if it's non-spontaneous to make it happen. So we're going to move on to a new thermodynamic term called Gibbs free energy. And Gibbs free energy comes from us playing with the basic delta S of the universe equals delta S of the system minus delta H of the reaction or the system over T the temperature. If we first multiply through by the temperature, I get T delta S T delta S of the universe equals T delta S of the reaction minus delta H of the reaction. Because remember, our system is a chemical reaction. Now I'm going to multiply through by a -1. So I have minus T delta S of the universe equals a minus T delta S of the reaction plus delta H of the reaction. Or rewriting that, delta H of the reaction minus T delta S of the reaction. Okay? Delta G is defined as equaling minus T delta S of the universe. So delta G equals delta H of a reaction minus T delta S of a reaction. Now, let's think about this for a second. Well, let me go back up here. If delta S of the universe is positive and we have a spontaneous process, delta G is going to be negative. If delta S of the universe is negative, non-spontaneous, delta G is going to be positive. So you can think of when delta G is negative from the point of view of the system, energy is being released, okay? And when delta G is positive, energy is having to be absorbed to make something happen. Now, let's look at a chart here. We can see with the delta G equation, delta G equals delta H of the reaction minus T delta S of the reaction. There are two things that influence whether a reaction is spontaneous or not. It's change in enthalpy and it's change in entropy. If delta H is negative, it's an exothermic reaction, and delta S is positive, so that we're having an increase in entropy, then delta G is going to be negative at all temperatures. So it's going to be spontaneous no matter what the temperature is. If delta H is positive, so it's endothermic, and delta S is negative, so we have a decrease in entropy, delta G is always going to be positive no matter what temperature. Those are the two easy ones. If delta H is positive, so it's endothermic, and delta S is positive, we have an increase in entropy. Those two things are opposites. Okay, they're working against each other. So the temperature plays a role. This kind of process is going to be spontaneous at high temperatures because T delta S is going to be larger than delta H, and it's going to be non-spontaneous at low temperatures. If it's exothermic, delta H is negative, and we have a decrease in entropy, delta S is negative, then again, temperature decides whether the reaction is spontaneous or not. At low temperatures, it'll be spontaneous because a minus T delta S, which is going to be a positive value, is going to be in magnitude smaller than delta H, and it'll be non-spontaneous at high temperatures. Okay? Now, Gibbs free energy under standard state conditions. There's a listing of the standard state conditions on page 815, but just remind you, partial pressures are 1 atmosphere. Things are in their standard state for the temperature we're dealing with. Under 1 atmosphere pressures, and if it's in solution, the concentrations are 1 molar. Now, just like delta H and S, we will find tables of delta G values, standard Gibbs free energy values. And Hess's law can be used for delta G just like we can use it for determine delta S of a reaction or define delta H of a reaction. So let's look at problem 18.8 on page 822 in your textbook. Let me find page 822. Okay, let me get things going here. Dr. Cam. All right, now let's look. Okay, one reaction that occurs with a catalytic converter in the exhaust pipe of a car is the stimulation of oxidation of carbon monoxide and the reduction of nitrogen monoxide, both of which are harmful pollutants. We got 2 carbon monoxides plus 2 nitrogen monoxides going to 2 carbon dioxides and nitrogen. Use the standard free energies of formation to get delta G of the reaction at 25 degrees. Okay, so you guys look at that. I'm going to write the reaction so that we can work with it. I've got 2 carbon monoxide gases plus 2 nitrogen monoxide gas going to 2 carbon dioxide gas and nitrogen gas. Okay, so that's our reaction. Now, let's look at our Gibbs free energy table. Okay, so we're going to flip to the appendices. Back here, we're going to go to Appendix A. Okay, now if we look at Appendix A here, I'm going to move this down. You can see the first column here is our delta H values, then our delta G values, and then our S values. Okay? Notice most of the delta G zeros of formation are negative. Some of them are positive, but lots of them are negative. So I'm going to start looking up the delta G values of formation for carbon monoxide, carbon dioxide, so on and so forth. So let's look at carbon dioxide. So let's find it. Carbon dioxide. Ah, there it is. Okay. Okay, guys. Carbon dioxide gas has a delta G of formation of minus 394.4 kilojoules per mole. So minus 394.4 kilojoules per mole. Okay, for carbon monoxide gas, it's minus 137.2 kilojoules per mole. Now I need to look up nitrogen and nitrogen monoxide. So find the N's, nitrogen and nitrogen monoxide. There we go. Nitrogen monoxide gas has a delta G of formation of 87.6 kilojoules per mole. And for nitrogen, just straight nitrogen, okay, find it, nickel. Nitrogen, it's 455.5. kilojoules per mole. Oh, that's just N, excuse me, it's 0. I was looking at in the atom instead of in the compound. All right, guys, so now we're ready to do some math. Okay, so delta G0 for the reaction is going to be the sum of the delta G zeros for the products times M, their coefficients, minus the sum of the delta G zeros for the reactants. And these are of formation. Okay? And there's an N there for the number. So I start with my products. I have 2 moles of CO2 times a minus 394.4 kilojoules per mole plus 1 times 0 minus 2 moles times a minus 137.2 kilojoules per mole plus 2 moles times 87.6 kilojoules per mole. Okay? Just make sure you got all of that. Give you a second to look. Okay. Now, if I pull out my handy dandy calculator, so 2 times 394.4 negative, so I have a minus 788.8 kilojoules minus 2 times 137.2 negative plus 2 times 87.6. This is a minus 99.2 kilojoules. So if I combine those, I get minus 689.6 kilojoules. Okay? When we look at that then, we get a delta G that is negative. Since the delta G is negative, it's a spontaneous process. Now remember, spontaneous doesn't mean fast. A catalytic converter catalyzes the reaction, which means that it speeds the rate of the reaction up. It's a reaction that would happen naturally, but in nature, out in the environment, is very slow to happen. You want it to be fast to happen, and that's why you have a catalytic converter. Okay? And they're pretty straightforward problems. I don't think you're going to have any issue doing those. You may get tired of doing them, but you're not going to have any issue doing them. Okay. Now, if delta G is negative, energy is being released by the process to be able to do useful work. And the magnitude of delta G tells you the maximum possible work to get out. Now, we never get the maximum, but that's the maximum possible. If delta G is 0, the system is in equilibrium, and you can't derive any energy from the system, and energy would be needed to move it away from this position in either direction. If delta G is positive, then energy is needed to maintain the system where it is, and it needs more energy to force it further in the direction indicated. Okay? So, for an energy releasing process, delta G equals works max. That's when delta G is negative. For an energy absorbing process, delta G equals work minimum, and it's a positive value. So remember, positive is non-spontaneous as written, negative is spontaneous as written, 0 means you're at equilibrium. Now remember, if a reaction is spontaneous in one direction, it would be non-spontaneous in the other. If it's spontaneous in the direction written, it's non-spontaneous in the reverse direction. Now, let me just remind you that for a lot of situations, there is what's referred to as a crossover temperature. For processes where delta H and delta S have the same sign, they're both positive or close negative, there's a temperature at which the reaction goes from being spontaneous to non-spontaneous. Okay? I'm not going to hit it too hard, but I just want to remind you that that's possible. Now, one of the things that we're interested in is how much energy we can get out of a system. Okay? And really, how much energy you can get out of a system depends on how far from equilibrium your system is. The further a system is from equilibrium, the more energy you can get out of it. The further you want to push it from equilibrium, the more energy you would have to put into it. Delta G tells us something about the reaction of the process under standard state conditions. But let's face it, most of the time when we're doing chemical reactions, we're not under standard state. We're not dealing with 1 molar concentrations for everything, or 1 atmosphere partial pressures. So we need to be able to determine delta G's for processes that are not under standard state. Okay? So let's remind ourselves about the big E, equilibrium. We know if Q is less than K, the reaction is written proceeds to the right. So it's going to be spontaneous in the direction written. Okay? If I looked at Q divided by K, it would be less than 1. This is when delta G is going to be negative. If Q equals K, we know we're at equilibrium. And Q divided by K would equal 1. Delta G is going to be 0. If Q is greater than K, the reaction as written will proceed to the left, which means it's non-spontaneous in the direction written. and Q divided by K is greater than 1, and delta G is positive, non-spontaneous. So there's a relationship between Q, K, and delta G. So let's look at what that relationship is. Turns out that delta G for any reaction is equal to RT, the ln of Q, over K, which equals RT, the ln of Q minus the ln of K. Under standard state conditions, Q would be 1. The natural log of 1 is 0. So we can say delta G0 is equal to minus RT ln of K. Okay, these are important equations. This one right here, okay, important. So we're going to look at problem 18.11 on 831. Okay, so page 831. Says calculate delta G0 for at 298 K for the reaction I2 plus Cl2 going to 2 ICl, and you're given Kp is 81.9, no units. Okay, erase the board here. So we're given Kp is 81.9, and we're told that the temperature is 298. And we're asked to find delta G0 for the reaction. All right, let's scoot over. Okay, so that's what we're working it with. Now, the equation we're going to use is that delta G0 is equal to minus RT ln of K now, R is the gas constant, but this time we want it in terms of joules. So it's 8.314 joules per mole Kelvin. So if I plug this in, I have a minus 8.314 joules over moles Kelvin times the temperature, 298 K, times the natural log of 81.9. Okay, let's make sure we got a good look at that. Now, if I use my handy dandy calculator then, 81.9 natural log times 298 times 8.314, and I take the negative of it, I get 1.09 times 10 to the 4 joules per mole. Because notice the Kelvin and the Kelvin divides out. Not bad. You can handle that. All right, so you guys take a look at that for a second. Okay, let me switch over to the computer. And bring you back over to see the screen. Okay, so we can take that equation and we go one step further. We can say delta G equals delta G0 RT ln of Q. So let's look at page 828. And we're going to look at problem 18.10. Okay, it says consider the reaction at 298 degrees for 2 H2S plus an SO2 going to 3 sulfur solid rhombic plus 2 waters gas. Delta G0 is minus 102 kilojoules. Calculate delta G under the conditions of partial pressure of H2S, 2 atmospheres, partial pressure of sodium dioxide, 1.5 atmospheres, partial pressure of water, 0.0100 atmospheres. All right, now you guys look at that. I'm going to rewrite the reaction. Okay, so I've got 2 H2S gas plus an SO2 gas going to 3 sulfur solid rhombic and 2 H2Os in the gas. Okay? And we're told that delta G0 is minus 102 kilojoules. And we're asked delta G. All right, guys, slide over here with me. Now, the equation we're working with is delta G equals delta G0 minus RT ln of Q. Okay? So, no, excuse me, it's not minus, it's plus. I always want to make it a minus. So to be able to do this, I've got to get Q. Now the Q expression is concentration, well, let's see, we were given partial pressures. So the partial pressure of water squared over the partial pressure of H2S squared times the partial pressure of sulfur dioxide. So if I plug these in, the partial pressure of water was 0.0100 squared. For H2S, it was given to us as 2 atmospheres. So 2 squared. And the sulfur dioxide was 1.50. Okay, so let's get Q. So 0.0100 squared divided by 2 squared divided by 1.5. Okay, do it again, 0.0100 squared divided by 2 squared divided by 1.5. Okay, I got the same thing twice, I believe it. I get a Q value here of 1.67 times 10 to the minus 5. Okay, so looking at plugging into our delta G equation, delta G equals delta G0. Now R is in terms of joules, delta G0 is in terms of kilojoules, so I'm going to convert it to kilojoules. So it's going to be 1.02 times 10 to the 5 joules plus R, which is 8.314 joules per mole Kelvin, times the temperature, 298 K, times the natural log of 1.67 times 10 to the minus 5. So I take the natural log of that times 298 times 8.314. So what I have is minus 1.02 times 10 to the 5 joules plus a minus 2.73 times 10 to the 4 joules. So 1.02 exp 5. So I get a minus 1.29 times 10 to the 5 joules. Okay. So the only trick to this problem is remembering how to write Q expressions, and you ought to be really good at writing K's and Q's by this point. And guys, that ends our energy chapter. Well, our energy chapters. And we're going to move on and look at electrochem next.